We're going to continue our discussion on acids and bases today, talking more specifically about the pH scale and how we use indicators to predict pH. The first thing I just want to note that there are certain ions that are associated with acids and bases. The OH minus ion is typically associated with bases, and that one is called the hydroxide ion, as you may recall when we went over table E. The H plus ion is called the hydrogen ion, and the hydrogen ion exists when you have an acid in water. And what typically happens is that the H plus ion associates itself with water, creating the hydronium ion. So these two terms are actually interchangeable. Now the pH scale, we typically discuss running between 1 and 14. pH of 7 is considered neutral. Water and salts are neutral, so they have a pH of 7. Numbers in the lower end of the pH scale, between 1 and 7, are considered acidic, and we'll talk about why those numbers are low shortly. And those in the upper end of the pH scale, between 7 and 14, are basic. Another term you may see describing that is alkaline. So if you see alkaline, that means basic. So something else that you should keep in mind is the concentrations of what the pH scale measures. A little tip that I give my students, pH, and I don't know if this is true or not, but it works well for a mnemonic device. I think of the P as the power of the hydrogen ion concentration. Now these are really, really small numbers, so small in fact that the power on the 10 in the concentration is actually negative. So let me give you an example. If we look over here at this table, this says at a pH of 1, we need to figure out what the concentration is. Well, the concentration is of H plus. By the way, that bracket means concentration. So by putting the bracket around the H plus, we're saying concentration of H pluses. The concentration is actually 1 times 10 to the negative 1 molar. So this pH number is actually this exponent right here. And to get this pH number of 1, we'd actually do the negative log of the concentration of the hydrogen ion concentration. So it's actually negative log of H plus concentration. Now nobody actually wants to do that, and you don't really have to in this case because this number is always going to be a 1 in Regents chemistry. If you go on to taking chemistry in college or college level chemistry here at Lockport, you will end up with concentrations where this is not a 1. But for our purposes, all you really need to do is take this exponent and leave behind that negative. Now, let's talk about why this ends up being the highest concentration of H pluses. And to do that, I'm going to skip down a little bit here, and we're going to look at these concentrations here. This concentration on HCl, if I convert that to scientific notation like we just did in the table, it will be 1 times 10 to the negative, and now I have to count my decimal places, 1, 2, 3, 4 to the negative 4th. So this one, the pH, is going to be 4. So that's where those numbers come from. So for this number up here, if I were to convert that to a decimal, it would be 0.1 molar. And when you compare this number here to this number here, now you can see why a pH of 1 is actually a much greater concentration than something whose pH is 4. So the smaller the number of the pH, the larger the concentration of H pluses. Let's go back up to the table and fill it in for the rest of the concentrations of H+. So back up here, if we have a pH of 7, that would mean the concentration is 1 times 10 to the negative 7th molar. So that would be a decimal, 6 zeros, and then the 1. So that's now the next one, we have 1 times 10 to the negative 14th molar. So again, that would be a decimal, 13 zeros, and then the 1. So that's a really small concentration of H+. This last one is 1 times 10 to the negative 3 molar. So sometimes we have to talk about a comparison between the H plus and the OH minus concentrations. And you learned in the last set of notes that typically H plus concentration is what we look at for acids and OH minus concentration for bases. As one goes up, the other one goes down, and vice versa. What that relationship really is if you were to take the concentration of H pluses and multiply it times the concentration of the OH minuses, you would end up with 1 times 10 to the negative 14. And if you remember, if you were to take, let's say, this example here, and we were to multiply those, so you have 1 times 10 to the negative 1 for the H plus concentration. And I'm going to tell you, this must be 1 times 10 to the negative 13. That's how you would get this number here, because when you multiply numbers with exponents, you add the exponents. So by knowing that this relationship is always just adding the exponents to get to that 14, you'll always be able to figure out what the concentration of OH minuses is if you're given H pluses or vice versa. So let's look up here at this example. We have the OH minus concentration given to us as 1 times 10 to the negative 4. So H plus must be 1 times 10 to the negative 10. So that the two exponents, the negative 4 and the negative 10, will actually sum up to negative 14. Let's continue in our examples below. We have this time H2SO4, and we've been given a concentration as a decimal. I'm going to first convert that to scientific notation. 1, 2, 3, 4, 5, 6. So my pH is actually 6. This next one's a little trickier because they've given us actually the concentration of the NaOH, which is the base. So we've been given 1 times 10 to the negative 3, but this is for the OH minus concentration. So my H plus concentration must be 1 times 10 to the negative 11, making my pH 11. I showed you that last examples and just in case they ever tricked you. So make sure before you decide you've figured out the pH that you've looked at what it is that they've given you. You may or may not have gotten to the point where you've done an example of a titration, but a titration is how you discover the concentration of either an unknown acid or an unknown base by finding the neutralization point when you know the concentration of the other. So essentially you're going to have 4 numbers. 1 you're going to be looking for, and 3 you already have. And you can see the equation for titration here in table T. You have MA and VA, which stand for the molarity of the acid and the volume of the acid, and that's set equal to MB VB, which is the molarity of the base and the volume of that base. So a titration, I'm just going to put the equation here, like so. If you look at the question we're given here, it says that we've been given a 4.0 molar NaOH. That is the molarity of the base, so I'm going to label that MB. And we're going to use 20 milliliters of that, that's the volume of the base, to neutralize 8 milliliters of the acid. So essentially, They've added 20 milliliters of a 4 molar NaOH solution to 8 milliliters that they measured of the acid and found the neutralization point. So we're going to use this equation now, that MAVA is equal to MBVB, to figure out the molarity of the acid. So we don't know MA. I'm going to leave that alone. VA was 8.0 milliliters. MB is 4.0 molar. And VB is 20.0 milliliters. So to get MAA alone, I'm going to divide. And that's essentially 4 times 20 is 80 divided by 8, or 10 molar for our answer. A lot of times students will get to the titration question on the exam, and because we're looking for a molarity, they attempt to use the molarity equation under concentration here to figure this out, and they don't have all the information they need and don't know what to do with those numbers. So make sure you actually read the question and don't just look at the numbers. Now we're going to talk about pH indicators. pH indicators actually change color based on the pH of the solution. To do this, we actually have a lovely table called Table M. I'm going to bring that in. Table M is set up a little odd, but it works. Methyl orange is said to change color in the pH range of 3.1 to 4.4. And it changes color from red to yellow, meaning that it starts out red and it becomes yellow on the other side of this. So between these two, it's actually orange, or the color between these two colors. So we're going to attempt to label this, and if you have colored pencils, you could make this really pretty, but we're going to attempt to label this with the colors that each of these indicators would be. So here is a pH of 1, 2, 3. So just over this, I'm going to draw a little line. So that's supposed to be at about 3.1. And over here it's red, and you could color that if you have colored pencils. And then right about here at about 4.4, it becomes yellow. And in between here, it is orange. Bromothymol blue changes in a pH range between 6 and 7.6. So here's 6 right here. And I'd say that's about 7.6. And it goes from yellow to blue. And as it's changing from yellow to blue, it is green in between. Phenolphthalein at a pH of about 8 to 9 goes from colorless to pink. So in here it would be light pink, I'm going to say, if I can fit it in there. Litmus changes between a pH of 4.5 and 8.3, and it goes from red to blue, and in between is purple. Brome cresol or brome cresol green at a pH of 3.8, so right about here, to 5.4. Might have gone a little far on that one. Goes from yellow to blue. So in between is green. And the last one on here is thymol blue. And all you guys have on your reference tables is that from 8 to 9.6, it goes from yellow to blue. So again, in between here, it will be green. If you've done the lab on indicators at this point, you'd know that there is actually another color change way down here, but no need to worry about that for the Regents exam since they won't ask you about that. All right, number 1, what could the pH range for a solution be that changes methyl orange and bromothymol blue yellow? So we could look up here. Oh, I'd like to move that a little bit. And you can see that methyl orange turns yellow starting right here, but bromothymol blue is only yellow to about here. So it's got to be somewhere between about 5.4 and 6. So that kind of blocks it in. Oh, is that not 5.4? It is 4.4, sorry, 4.4 and 6. Kind of blocks it in a little bit there. So we're going to put 4.4 to 6. If bromothymol blue is added to a solution with a hydronium ion concentration of 1 times 10 to the negative 8th, what color would this solution be? Well, this is a pH of power of hydrogen of 8. So bromothymol blue, if you're using this one, at a pH of 8, that's right here, so that would be blue. Or if you were starting to get used to using this, you would look bromothymol blue. 8 is above this range, so it would have to be blue. What could the pH of a solution be that changes bromothymol blue to blue and phenolphthalein remains colorless? Let's try doing this with just this. So bromothymol blue is blue above 7.8 according to this chart, but phenolphthalein is only colorless to a pH of 8. So we're going to say it has to be between 7.6 and 8. That's a really tight range. Number 4, use 2 indicators to verify the solution or the pH of a solution is 7.8. So let's see if it turned bromothymol blue blue. Oh, we would use the same example, or phenolphthalein colorless. Or if you wanted to, you could say litmus would be purple and bromothymol blue would be blue. That could do it too. So we're going to say, so that it's something different, bromothymol blue we're looking for that to be blue. Therefore, it would be greater than 7.6. And we would look for litmus to be purple, so that it has to be less than 8.3.